Hey, I'm glad you're here. I've been flipping this coin and getting some really weird results. Check it out. I flipped this coin 10 times and gotten 8 heads. That's 80% heads and 20% tails. Not what I was expecting, since I thought this was a fair coin. Grab your own coin and we'll talk more about probability distributions. If you haven't done the pre-video activity, pause and complete it now. All done? Let's put our coins to the test. What would we expect from a fair coin? In other words, what is the theoretical probability? Well, since there are two sides, we would expect that 50% of the flips are heads and 50% are tails. So what's the deal with my coin? Well, an important point to remember is that probability describes what happens in the long run. It does not guarantee a certain outcome in an experiment. So, in the long run, when I flip a coin, I would expect 50% of the results to be heads and 50% tails. So, what would happen if I flipped the coin 10 more times for a total of 20 flips? Would the results be different? Pause now. Flip your coin 10 more times and record your results in your guided notes. My results are looking a little closer to the theoretical distribution with 65% heads and 35% tails. How about yours? Let's try another 10 flips for a total of 30 flips. Well, it seems to be evening out even more with 60% heads and 40% tails. I'm feeling less skeptical about this coin now. What do you think would happen if we were to flip the coin 100 times? 1,000 times? As we flip the coin more and more times, it will likely keep getting closer to 50-50. What we've demonstrated here is something called the law of large numbers. This law states that as the number of trials increases, the closer the experimental probability gets to the theoretical probability. Let's add some other factors to our coin flipping and use the law of large numbers to help us discover more about the probabilities at play here. Let's say that you're playing a game where you get $1 for every tail that occurs when you flip a fair coin 3 times. The catch is that you have to pay $2 to play. Take a moment and consider your instinct about this game. Do you think it's worth it to pay $2 to play this game? Pause and record what you think. To answer our question, we need to determine, in the long run, what we can expect to happen each game. In other words, we want to know the average outcome. Just like our coin flips started reflecting the theoretical probability over many trials, our average results in this game will also settle into a predictable result.
Let's first consider the outcomes. In this probability distribution, X is the amount of money you receive playing this game. Since you could flip 0, 1, 2, or 3 tails, we could earn 0, 1, 2, or $3. In the last lesson, we completed this probability distribution in both tabular and graphical format. From looking at the table and graph, how much money can you expect to win on average when you play this game? Make a prediction before we calculate it together. The average of a probability distribution is also called the expected value. The expected value is the weighted average of the outcomes of a random variable. It tells us what outcome we'd expect to occur over a long period of time or large number of trials. Mathematically, the expected value is calculated by summing each possible outcome multiplied by its probability. Applying this formula to the coin game, we can calculate the expected value as 1.5. That means, on average, you can expect to win $1.50 per game. But how does this actually work? We can't win exactly $1.50 in one round of this game, right? The law of large numbers tells us that if we repeat an experiment like this game enough times, the actual results will get closer and closer to the results we expect based on the theoretical probabilities. So while we might not win exactly $1.50 every time we play, over many games, our average winnings per game will settle around that number. Now that we've found the expected value of this game, what do you think? Is this game a good deal? Remember, you pay $2 to play each time. That means on average, you're actually losing 50 cents per game. Not the best deal, huh? How was your intuition about this game? You may have even predicted the exact expected value by looking at the probability distribution in graphical form. Because the distribution is perfectly symmetrical, the mean is directly in the center. What about this distribution representing a modified version of the coin game? What do you think the expected value might be? Because this distribution is skewed right, we might expect the mean to be here, somewhere around 2. Let's find the expected value to see whether this game is a better deal. In this modified game, the coin is still flipped 3 times, but it's a weighted coin. The probability of flipping tails is less than the probability of flipping heads, but you get $2 every time you flip a tail. Find the expected value of this modified game. First, we multiply each value of x by its probability, then add up all of those products. For this game, the expected value is $1.80. A bit better than the last game, but still less than what we would pay to play. Great work! Let's wrap up with one more example. A used bookstore has a backlog of inexpensive books they want to clear out. So they're creating a mystery book promotion. To make it exciting, they're mixing in some newer, more valuable books with the older, cheaper ones. They plan for 80% of the mystery books to be worth $2 each and 20% to be worth $10 each. The owner wants to price each mystery book so that, on average, they break even. Let's set up our probability distribution. We'll define the random variable y as the bookstore's profit per book. We still need to determine how much it will cost to buy a mystery book. We'll call that x. The profit for each $2 book would be x minus 2, and the probability of selecting one of those books is 80%. The profit for each $10 book would be x minus 10, and the probability of selecting one of those books is 20%. If they want to break even with this sale, they don't gain anything or lose anything for each book sold. In other words, the expected value is $0. Pause now and determine the value of x such that the expected value is 0. Using the formula for expected value, we can set up the equation 0.8 times x minus 2 plus 0.2 times x minus 10 equals 0. Solving for x gives us a value of 3.6. So what does this mean? For the bookstore owner to break even with this sale, they should charge $3.60 per book. Today, you learned 2 key probability concepts. The law of large numbers, which explains that as we increase the number of trials, our results get closer to the true probability. And expected value, which helps us understand the long-term outcomes of a random variable. These ideas are essential for making sense of data and uncertainty in real-world scenarios. Make sure you finish up your guided notes before moving on to the lesson activities. Then, complete the online practice. See you next time.
Hey, hey.